Hello, everyone, and welcome to our short course. My name is Wei Fu. I'm a geomechanics engineer with ITASCA, and my work is mainly focused on continuum and discontinuum modeling for geomechanics and fluid flow problems. In the first section of today's course, I will provide an introduction to numerical modeling. This is a big topic, so here I will briefly talk about what numerical modeling is, different numerical methods, advantages and disadvantages of different modeling approaches, as well as general modeling considerations and modeling strategies. First of all, why do we want to discuss numerical modeling in this course? So in the later section of today's course, I will give an example of surrogate modeling using the synthetic data from numerical models, which provides a faster way to make predictions. And in this process, we want to ensure that we train the machine learning models with meaningful input data. So it is necessary for us to go over some numerical modeling concepts to lay the foundation. Also, numerical modeling actually shares some interesting similarities with machine learning approach, which can help us understand both approaches. For example, they are both a representation of a system using mathematical models. And these mathematical models can either be the governing equations in the numerical modeling approach or different algorithms in the machine learning approach. And they both try to predict and approximate the reality. So in such problems, convergence is very important. And to achieve convergence in the numerical modeling, for example, we will try to minimize the unbalanced force in order to reach the equilibrium state. And in the machine learning approach, we can minimize the loss function, which measures the difference between predicted value and the actual value. And there have been questions about whether these approaches are black boxes. Well, for numerical modeling, the models are based on rigorous governing equations and numerical methods. And for machine learning models, they're based on mathematical optimization with different algorithms and structures. So in this regard, they're not really black boxes. However, both approaches are also becoming more and more complex. We know a numerical model now can have millions of elements or particles with different components interacting with each other. And you can also have different effects. For example, thermal, chemical, creep, fluid. So it can be very complex. Well, the machine learning models go further in terms of complexity. We know ChatGPT-3 has about 200 billion parameters, and ChatGPT-4 has trillions of parameters. So for both approaches, it's becoming increasingly hard for users to know what's going on inside, which is why it is very important for us to understand the fundamental concepts and algorithms while using these methods. Now let's talk about numerical modeling. Numerical modeling is a simulation of real-world systems using numerical methods. And here's a quote from Dr. Box. All models are wrong, but some are useful. So it tells us that no models can perfectly represent the complexities of the real world. And this is really because a numerical model is an approximation, not reality. So there are always limitations and uncertainties which will require some sort of simplifications. On the other hand, well-defined numerical models can still provide us with valuable insights and help us to make predictions. And we can use numerical models to quickly investigate different scenarios that cannot be otherwise easily evaluated. And here is another quote from Dr. Starfield and Dr. Kondo. By the way, Dr. Peter Kondo originally developed the discrete element method, and he's the co-founder of ITASCA. Numerical modeling should be an aid to thought, not a substitute for thought. So critical thinking and conceptual understanding are important to guide our numerical modeling efforts. And lastly, for reliable numerical modeling, we would need appropriate constitutive models or contact models. Here is an overview of the numerical methods. These categories can also be defined based on other criteria. For example, whether the approach is meshless or not. Here, based on different applications, we can divide the numerical methods into two categories, continuum methods and discontinuum methods. For the left-hand branch, the continuum side, you can discretize the domain using surface mesh, which corresponds to the boundary element method. And you can also discretize the domain using volume mesh, which will correspond to three classical methods, the finite element method, finite difference method, and finite volume method. These methods are powerful in solving differential equations. And we know that many processes in nature can be described using differential equations. For example, the gradient in air pressure generates the wind, and the gradient of particle concentration leads to the process of diffusion. But many of these differential equations, particularly partial differential equations, they are extremely difficult or not even feasible to solve analytically. For example, the Navier-Stokes equation, which is $1 million problem. So with the help of these numerical methods, we can discretize the domain into either grid nodes, finite elements, or controlled volumes. Then we can convert differential equations into a system of linear algebraic equations. This is done by either converting the derivatives of a quantity into quotients or taking integrals of the governing equations. By doing this, the differential equations become much easier to solve. Then depending on how the differential equations are solved in the time domain, the numerical methods can be further divided into implicit methods and explicit methods, which I will discuss later. And on the right-hand side is the discontinuum approach. Examples include the DDA code, which uses an implicit scheme, and the particle flow code, PFC, which uses an explicit scheme. These methods solve the movement and deformation of particles or pieces based on Newton's law of motion and contact laws. And I'll provide more examples in the following slides. Here are some examples of ITASCA codes for continuum and discontinuum modeling. On the left is an example of flag in flag 3D, in which the materials are represented by a continuum of zones, and the stress-strain behaviors are defined by constitutive models. It is possible to include a few fractures in a continuum model, which are represented by interfaces, and the interfaces can slip and separate. Then we have the UDEC and 3DEC codes for modeling jointed systems in 2D or 3D. In these codes, materials are represented by a network of blocks, and they are cut by discontinuities. These blocks are able to rotate and slide along joints, and the joints can open or close. And within each of the blocks, the material can deform following constitutive models as a continuum. So it is really a hybrid between discontinuum modeling and continuum modeling. Then we have the PFC code, which is a DM program. So in PFC, instead of using zones or blocks, it uses bounded or unbounded particles to generate synthetic materials, and it models particle movements and interactions at soft contacts. In PFC, the microscopic behaviors of materials are emergent. For example, in a compression test, the macro cracks can develop and eventually merge into a shear fracture. And the last one is Explicit, which is a lattice-based DEM code. Explicit is developed based on PFC, but instead of using the particles and contacts in PFC, in Explicit, the materials are simulated by lattice nodes connected by springs, and the springs can fail to form macro cracks. And you can also insert smooth joint model in the domain to simulate discontinuities and natural fractures. Explicit is designed for hydraulic fracturing applications, and it runs much faster than PFC. Now let's talk about explicit and implicit methods. They are used to describe how differential equations are solved in the time domain. The explicit methods calculate the solution for the next time step based on the values of the current time step. And the implicit methods solve the governing equations using the values of both the current and the next time steps. Also, implicit methods need to solve the complete system of equations at each time step, while the explicit methods only solve the local equations for each point based on its nearest neighbors. And because of this, the implicit methods can be more computationally intensive. And as you can see on this plot, which shows the change of the calculation time with model size. And the time required for explicit methods increase linearly, but the calculation time for implicit methods can increase much faster as the model size increases. The ITASCA code, such as PFC, FLAG, and 3DEC, they all use explicit solution scheme. And in general, explicit scheme is more efficient for problems that have highly nonlinear behaviors, large strain, and dynamic response. And also, as you can see in the upper right plot, explicit methods in general applies to a larger scope of scenarios. Let's look at the advantages, limitations, and the solutions to the limitations for different methods. And we'll start with the continuum modeling. So why is continuum modeling popular? Well, first of all, it's fast, meaning it can support the simulation of large-scale applications. So you can run the model with millions of elements on a regular personal computer. And the largest model I built in Flex3D has about 28 million elements, and it runs on a personal computer without problems. And because it has been around for a long time, it is mature in terms of different modules and functionalities, such as fluid, thermal, structural elements, which can be found in most continuum codes. Here are some examples in Flex2D and Flex3D. So you can start from a 2D model and have increasing levels of complexities. You can consider different features, such as geological layers, and you can have different topographies, different faults, and you can include underground constructions, such as tunnels, and you can also add different structural elements, such as rock bolts. Another advantage is that you can directly specify classical constitutive models, such as the Moore-Coulomb model or Hook-Brown model, and you can also implement your own model. For example, developing a user-defined model in Flex3D. There are also limitations of the continuum approach. For example, the continuum assumption can become invalid or less accurate under certain conditions, such as the rock fracturing and rock blasting applications. And they can only handle a limited number of interfaces or discontinuities. For example, in Flex3D, it could probably handle about 20 to 50 interfaces, but if you want to include more, it can become challenging. And the efficiency in modeling the interfaces will drop a lot when the contacts break plastically. The natural development of cracks and ruptured surfaces are not well handled by continuum approaches. And lastly, although classical constitutive models are available to use, they could be oversimplified because actual rock mass is heterogeneous and anisotropic in nature. And in this regard, an appropriate stress-strain law for the rock may not even exist. There are a few ways to deal with the limitations of continuum modeling. And if there are only a few joints, you can include the joints explicitly in the simulation. And here is an example of a simple model with a couple of joints in it. And this is a continuum model. You can see all of these deformations developing the zones, and the upper region is sliding along the joints. When there are a lot of discontinuities in the rock mass to consider, such as fractures, faults, joints, and bending planes, a very common approach is to use the equivalent continuum approach. This is to simplify the analysis of rock mass by treating them as continuous materials with averaged mechanical properties. For example, in Hook-Brown model, different geological strength index can be chosen for jointed rocks, and a lower GSI corresponds to poor rock mass quality with a higher number of discontinuities. At ITASCA, we also have this ubiquitous joint model, and here is an example of it. All of these blue disks are not explicitly modeled joints, and the model is still a continuum model, but we can embed this uniformly distributed slip planes in a Moore-Coulomb material, such that the rocks behave as if there were many joints. Another option is to develop a new constitutive model that can better describe the behaviors of rocks. For example, the MS model, which stands for ITASCA Constitutive Model for Advanced Strain Softening. This model can account for the evolution of rock deformation and failure from the intact or jointed condition to a bulked material. You can also write your own constitutive model and use it for modeling. Now let's take a look at some advantages of the discontinuum modeling approach. First, it is well suited for modeling the discrete nature of a system. For example, this movie shows the material flow in the mixer. And here is a Brazilian test in PFC, which shows the fracturing due to the damage and macrocrack accumulation in a rock sample. Also, discontinuum approach is capable of modeling a large number of fractures. And here's an open pit model that I built in 3DEC. It includes hundreds of explicitly modeled joints intersecting each other with different mechanical properties. In addition, the pieces or particles in these models can move, separate, and rotate, which can lead to realistic bulking and spalling behaviors. So you don't need to specify complicated constitutive models, and these behaviors are emergent. There are also some limitations of the discontinuum modeling, which in our case apply more to the PFC model, because the 3-deck or U-deck model is essentially a hybrid approach. Firstly, it requires calibration to match the microparameters. Also, it is very slow to simulate field scale problems because you need to use massive number of particles. So how do we get over these limitations? Well, there are a couple of possible solutions here. One way is to couple the discontinuum model to a continuum model to do the field scale simulation. In this way, we can simulate a much smaller region of interest using the discontinuum approach, which allow us to study complex damage and failure behaviors of rocks. And for the rest of the domain, you can simulate it with the continuum modeling approach. And here is an example of coupled discontinuum and continuum approach. This is a multi-stage tunneling model in PFC 3D. The model is formed by flat 3D zones for the majority of the domain. And here we have a thin layer of PFC bounded particles embedded in the flat 3D model across the direction of the tunnel excavation. The bounded particle microparameters have been calibrated to match the mechanical properties of the flat 3D zones. And here the contour shows the displacement field for both the zones and the particles. They have the same range for direct comparison. So as you can see, during the excavation of the tunnel, the transition between the behavior of the zones and the particles is smooth and is continuous across the coupling boundaries. Another way to speed up the simulation is to use the lattice approach, which is a simplified DEM approach with much greater computational efficiency. One example of lattice model is ITASCA's Excite code. So instead of using the spheres and contacts of PFC, we replace them with point masses and springs. Those springs can approximate the elasticity of the rock mass, and they can fail and form microcracks. And these microcracks may merge and form microfractures following a fracture propagation criterion. This approach makes the computation much less intensive. And in Excite, we can include thousands of pre-existing joints or DFN in one model. The plot here shows an Excite model of fracture propagation from 3 perforation clusters within one stage, and the well is located in a multi-layer formation. And the left plot shows the fracture aperture, and in the plan view plot on the right, you can see the fracture geometries becoming non-planar because of the stress interference between the hydraulic fractures. And this is the field scale simulation. And with Excite, you can also look at small scale problems, such as studying the near wellbore tortuosity by explicitly modeling the perforation holes. Now let's talk about some general considerations when constructing numerical models. So when to use numerical models? Here the plot shows the evolution of design-based processes for geotechnics. The vertical axis shows the level of reliance for different tools and methods. As you can see here, the methods for subsurface investigation have been evolving over the years. A century ago, people mostly rely on engineering judgments in situ testing and laboratory testing. And the dependency of each methodology varies as new technologies become available, such as numerical simulation and probabilistic modeling. So among these different methods, when do we use numerical models? So in general, there are a few situations when you should consider using numerical models. For example, when empirical methods become unapplicable to new situations, or the analytical models are oversimplified and can lead to underestimation of the actual solution. And when there are limited lab data or field measurements, numerical modeling will be helpful to predict behaviors, test hypotheses, and fill in the gaps where the data or measurements may be lacking. In addition, numerical models are particularly useful to understand complex physical behaviors that cannot be easily solved, such as rock collapse. And lastly, compared to physical tests, it is in general more cost-effective and time-efficient to run numerical models. Although we can build large, complex 3D numerical models using different codes, it is still worth thinking about whether the models can be simplified, particularly when generating data for surrogate modeling. we would need a large number of numerical models to form the training dataset. In this case, it becomes crucial to understand how to properly simplify the numerical models while still capturing the key behaviors. A good way of simplification is to reduce the model dimensions from 3D to 2D. For example, flag 2D modeling assumes plane string condition, which is useful when you have very long structures in one dimension. Then you can only simulate a slice of it. In plane string conditions, the assumption is simple. The out-of-plane string is 0, which means there's no deformation in that direction. And here are some scenarios when you can use the plane string assumption. In general, 2D analysis is faster and simpler than 3D analysis. It is also particularly useful for conceptual understanding and in cases when extensive parametric studies are needed. So always think first, is the 2D analysis suitable for the problem? And in the scenarios when the key features of the model are in 3D, for example, when you are modeling jointed rocks or tunnel intersections, a few other scenarios are when the material has anisotropy in out-of-plane direction, where in situ principal stresses are not perpendicular or parallel to the axis of interest, or the displacements and acting forces have components in all three directions. A 3D analysis should be used instead. Another thing to consider is the model symmetry, which can significantly simplify numerical simulations. So when there are symmetrical boundaries in a numerical model, consider imposing the symmetric conditions on these boundaries instead of modeling the entire domain. For example, for a structure that is symmetric to both x-axis and y-axis, you can only model a quarter of it and apply roller boundary conditions along the line or plane of symmetry. This would allow you to model the same problem, but with much less computational time. It also allows you to use a finer model resolution. But again, be careful if there are discontinuities in the domain, which may break the symmetry assumption. In general, when the stress distribution is uniform and the material properties do not vary significantly throughout the domain, a 2D model would be suitable, which can simplify the analysis and achieve accurate results. Then, if there are varying stresses and varying materials for different regions, you may still use 2D models, but use several of them. By doing this, you can address different regions of interest with different material properties and stress distributions, and still benefit from the computational efficiency of the 2D simulations. But in the case when the model has complex geometries, varying stresses, and varying materials, a 3D model would be needed to capture the full behaviors accurately. And lastly, although we can always build complex 3D models, I would still recommend at least going through the thought process about modeling complexity, because it not only helps simplify the numerical simulations, but also help identify the dominating influencing factors and parameters of interest. Here is another important concept, which is the model size. The goal here is to decide the model boundaries such that the model is large enough to capture the behaviors correctly. There are two types of boundaries in a numerical model. One is the natural boundary, such as the free surface of the Earth. The other one is the artificial boundary, which are the numerical boundaries that you impose on the simulation domain. In principle, the artificial boundaries should be placed far away from the area of interest to minimize their influence on the results. So if the phenomena of interest interact with the artificial boundaries, such as the plastic flow or joint sliding, it would invalidate the solution. And here is a sketch of a tunnel with plastic zones developing around the tunnel. As you can see, the boundaries are too close to the tunnel, and they interact with the plastic deformations, so the solution will be wrong. Similarly, for the slope stability problem here, when the artificial boundaries interact with the failure plane, the modeling would give wrong results. On the other hand, putting the boundaries too far away would lead to excessive computational cost. So in many cases, you may need to perform sensitivity analysis to determine where to put the boundaries. Let's look at an example of the stress distribution around a circular hole. You can calculate the stresses from the Kirsch solution. As you can see, the stresses are a function of the distance from the excavation center. And if you put the boundaries at the location where the distance is about 2 times of the radius, the stress is still changing in this region, and the solution will be incorrect. So you will need to have the boundaries beyond such regions where stress has big gradients due to the engineering disturbance. In this case, as a rough guide, you can use a boundary to object size ratio of at least 5. Now lastly, let's walk through the workflow for the numerical analysis. Step 1, define the objectives for the model analysis. So ask yourself, why am I building this model, and what are the answers I'm looking for? Normally, numerical models are used to determine mechanisms when there is limited or no data. When the geology is simple and it has detailed site investigation and complete information, the numerical models can also be used for predictions. Then step 2, create a conceptual picture of the physical system. So like what I discussed earlier, think about 2D models or 3D models, geometry symmetry, model boundaries, and what are the major geological structures, and should we consider other effects such as groundwater, creep, dynamics, and thermal effects. Then step 3, construct and run simple idealized models even before the data is available, because this helps us to understand how the system behaves and give us a better picture of the numerical modeling scope. And it can sometimes help initiate the recollection of data. And if the results do not correspond to what you think, try to understand it instead of further confusing the results with model complexity. And step 4 is to assemble problem-specific data, such as geology, geological structures, material properties, in-situ stresses, pore pressure, and other data. Now with the data and what we learned from simple models, we can prepare a series of detailed model runs and perform the model calculations. We can include monitoring points and histories to look at the model's response and convergence rather than only relying on the final state. And always remember to save the model regularly. And lastly, the post-process and interpret results. We can monitor the changes in parameters such as displacement, velocity field, and failure state, and determine the status of the model. Let's say if you are looking at a slope model in Flight 3D, if the velocity in the simulation domain is all small and random, then the model likely reached equilibrium. However, if you see coherent velocity field like this, it means your slope is failing. You can determine what is happening depending on structures like this. You can also monitor the displacement and unbalanced force. For example, if the displacement becomes stable or the unbalanced force approaches 0, then it means the model comes to equilibrium. The interpretation is a critical step, and it requires a combined understanding of numerical modeling and the underlying mechanical behaviors. So here is the summary of ITASCA's numerical modeling applications in different areas. We do numerical modeling in a wide range of fields. Here you see civil engineering, such as dam stability, tunneling, and foundations, and in environmental engineering, such as the modeling of groundwater, chemical transport, and waste isolation. We also model the material mixing, sorting, and segregation in the area of manufacturing and materials. We also do simulations in mining, such as open pit mining and cave mining, and in oil and gas, such as wellbore stability and hydraulic fracturing, and also in the area of power generation, such as power infrastructure and enhanced geothermal systems. So if you have any modeling questions or would like to know which modeling approach to start with for your projects, please feel free to reach out to us, and we are happy to help. And that's all for today's introduction to numerical modeling, and thank you for your attention.